13 ነው።
በቃ መጀመር እንችላለን።
13 ነው።
ሶ 13 ሰው ነው። So now our last topic of this course is aircraft engine component matching and of design analysis. So this is one of the vital part of the aircraft propulsion course because it connects each of the components together, and the performance of one of the part affects another. So that effect is directly connected with this topic. So let's start with the aircraft engine component matching, what it means. So component matching ensures that all engine components operate together at a common mass flow, because the mass flow rate is through all the components, starting from the inlet, going through the compressor, then combustor, again turbine, nozzle, and other components. So all the engine components are directly affected, so that matching is required for this purpose. Okay, so as we know, the gas turbine engine consists main components like inlet, compressor, combustor, turbine, and nozzle, or the exit section. Okay, so and each component has its own performance map, and matching finds a point where they are all compatible. So compatibility is the main issue here. In component matching, we expect compatibility of each of the components in the engine components. Therefore, why component matching is required? Component matching is important because it ensures that all engine components operate together safely, efficiently, and stably under the same operating condition, and which ensures stable engine operation. Stable engine operation related with proper matching, which prevents compressor surge and stall. Again, power balance between components is required. The turbine must produce exactly the power required by the compressor and by the fan. So power balance is another issue why we are performing component matching. Common mass flow and pressure compatibility is also required. The mass flow of air and fuel mixture, which is what we call stoichiometric ratio. So all components must handle the same mass flow and pressure level. Mismatching that occur in any of them will cause a shock and loss or instability in the engine. That instability is related with the engine surge and stall. Again, we need component matching for safe operation across operating range. So matching ensures the engine operates safely at design and off-design conditions, such as like takeoff, climb, and the cruise. As we know, all the flight mission profiles need safe operations, starting from the engine startup up to the run in the runway, again takeoff, cruise, land, descent, climb, and then finally landing. All needs an appropriate matching of the components and work proper or safe operation. Another is define the engine operating lines. So component matching determines the operating line on compressor and turbine maps, ensuring adequate surge margin. That stall margin must be defined. And what are the key parameters which affect the off-design flight conditions? Among them, altitude is the one. So the altitude of flight is related with the pressure, temperature, and the density. Okay, as we climb up and up, the temperature decrease, pressure also decrease, temperature also linearly decrease. So this affects the performance. so that it influences non-standard ambient pressure, air density, and temperature, and such as actually this is the main parameter. Again, flight Mach number, the in which flight speed we are flying. Rather, flight Mach number, we can say flight speed. In different phases, we use different flight speed. So various phases of the flight, like takeoff, climb, cruise, landing, which needs different flight speed. Okay. So another, the throttle setting. The throttle setting is related with the nozzle parameters, like turbine entry temperature, the throttle exit temperature, pressure. Again, after Barnell setting and the nozzle area ratio. So area ratio is one of important factor in optimizing the installed thrust. So we are familiar with the installed thrust because we already developed an equation for installed thrust. What are the laws which govern the engine component interaction? Among the laws, one of the important law is the law of conservation of mass, that the mass flow in to the system should be equal to the mass out of the system, which is known as the continuity equation. So in a steady state operation, the mass flow rate, that is the mass per unit mass per second, through a component must be equal to the mass flow rate delivered to the next component. So the mass flow in each of the components must be balanced. And the air mass flow rate through the inlet must match the fan mass flow rate, and others also same condition. So that is what called component matching. The second governing law is the law of conservation of energy from our first law of thermodynamics. So which states that the work done by the turbine, which is equals to work done by compressor plus work done by fan. So the turbine shaft power output must be delivered to the compressor and accounting for power extraction. And the frictional loss in bearings should be considered. Okay. And the compressor and the turbine stage on the same shaft must operate at the same angular speed. So the angular speed of low pressure compressor is equal to the angular pressure of low pressure turbine. And the angular speed of high pressure compressor is equal to angular pressure of speed of high pressure turbine. This is actually in the case of two spool machines, or in the case of two spool engines. The third is conservation of atomic species, that what we have discussed in the last chapter. So it allows for the variable gas composition through the components, so that atomic species should be conserved. So the gas composition changes due to temperature drop during turbine expansion with equilibrium gas chemistry principles, which establish the gas composition at each operation condition. Therefore, the gas constant, gamma, R, and the Cp. Okay, gamma is the Cp over Cv, R is the gas constant, universal gas constant, and Cp is the specific heat at constant pressure, which are specified per component, entrance and exit conditions. Okay, and also categorized into three sections. So we have actually cold section, we have hot section, and very hot section. So as you see from this picture, you can observe cold section from the inlet side. The intake and the compressor are considered as cold section. And after that, in the combustion chamber, we can observe the hot section. And then after the combustion products move towards to the what you call the turbine, around turbine and exhaust, we can see more hot section or very hot section, like in the afterburner and the nozzle sections. So that is based on the atomic species conservation. Again, the law of conservation of momentum also be conserved here. As we know that change in momentum of exhaust gas produce thrust. So the thrust production is due to the momentum change. And the governing interaction between engine and aircraft are the thrust force, which is mass flow rate, which is mass of air plus mass of oxidizer, no, mass of fuel plus mass of oxidizer times exit velocity minus inlet velocity. Plus, we have exit pressure minus ambient pressure times the exit area. So that is the momentum conservation principle, and which is used to balance force magnitude and direction produced by each component. But in the steady state matching, mass and energy interactions are more critical than the conservation, the momentum. Therefore, when we summarize this topic, engine component interaction is governed by conservation of mass, conservation of energy, and the conservation of momentum. Again, thermodynamics laws, gas laws, and mechanical equilibrium all should be stable, ensuring stable and efficient engine operation. So, another important topic here, what we are going to proceed is engine corrected parameters. So how we can correct the engine parameters? The engine corrected parameters are simply a normalized variables. They are normalized variables used in the gas turbine engine performance analysis. Okay, so they allow engine components to be compared and matched under different operating and of design condition. So under this, we can see about 5 engine corrected parameters. One is corrected mass flow rate. Second is corrected shaft speed. Third is corrected fuel flow rate. The fourth one is corrected thrust. And finally, corrected thrust specific fuel consumption. So these parameters, we will see them one by one under the next topic in the preceding section. So the first one is engine corrector. Actually, to analyze the engine corrector parameters, we have to observe this figure. So this figure, we already seen this figure in the chapter 2, where we developed the engine thrust. The equation of engine thrust being developed from this equation, from this figure. On that, we have the free stream condition 0, starting from 0 to the inlet condition at 1, and finally exit condition at 9. So this is already there in your previous chapters. So in order to define, we have to define the reference pressure and temperature. So in our case, the reference pressure is the 1 atmospheric pressure, which is 101.33 kilopascal, and the reference temperature is 288.2 kilo Kelvin, respectively. These are the reference conditions, which is actually nearly 15 degrees centigrade temperature and 1 atmosphere. So based on the this reference condition, we define the parameters delta and the theta for station I. I station means any stations among, it can be 1, it can be 2, 3, 4, 5, maybe station 9, or it can be 2.5 or 4.5. Okay, so I is different stations within the engine. So delta I indicates the pressure ratio. PTI, pressure at any section I, total pressure at any section I divided by reference pressure is given delta I here. So these values are useful for the next, the preceding section, so that you have to understand what is delta I, what is theta I. And when we define theta I, it is the ratio of temperature. at any reference point, any point I in the engine divided by reference temperature, which is 288.2. So based on that, we'll proceed our discussion. So the first corrected factor is corrected mass flow rate, or M dot C. So the correct mass flow rate and corrected shaft speed are the parameters that fully describe the behavior of compressor or turbine. Now, the first one is corrected mass flow. So corrected mass flow MC dot. Hello? Hello?
ይሰማል ዶክ?
ተቋርጦ
ይሰማል ዶክ?
ነበር አይደለ? መሀል ላይ
አዎ ተቋርጦ
አዎ
ነበር።
ተቋርጦ ነበር።
ግን ኦኬ፣ አሁን እንትኑ ይታያቸዋል ስላይዱ።
ስላይዱ አይታይም።
ኦኬ፣ ሼር ላድርገው። እሺ፣ ኦኬ፣ አሁንስ
አሁን
አሁን
ቪዚብል ነው።
ይታያል።
okay, fine. So the corrected speed, corrected mass flow is the one among the correct parameters. So which is defined in terms of the actual mass flow, MI, times the temperature ratio divided by pressure ratio. Okay, so T reference indicates the reference temperature, and the T naught is the free stream temperature, the air or free stream temperature condition. And P naught is the free stream pressure condition. P reference is the reference pressure condition. Okay, so MC is related with the actual mass flow rate, M by temperature ratio divided by pressure ratio. So the mass flow rate at station I is the mass flow rate at station I at the reference pressure and temperature. Therefore, MCI, the correct mass flow rate at I station is equal to the actual mass flow rate at I station times theta I divided by delta I. So we already defined theta I, temperature ratio, and delta I is pressure ratio. So temperature ratio divided by pressure ratio. Therefore, this can be rewritten as with the help of those gas constants. Gamma I, Ri, actually Ri is constant. We have that 287.05 joule per kilogram Kelvin. So Ri over gamma I over Ri under radical times pressure, reference pressure divided by radical of reference temperature times area of I section times Mach number of I section, the whole times 1 plus gamma minus 1 over 2 mi square, the whole times minus of gamma I plus 1 over 2 times gamma I minus 1. So this is just relating all the thermodynamics principle. We will get this equation. Okay, so actually these representations are representations for mass flow rate. The second is corrected shaft speed or rotational speed, NC. So NC in the RPM, revolution per minute, actually. Corrected rotational speed or RPM, NC is equal to N times radical of temperature reference divided by temperature naught. So this is NCI over N divided by theta I. It is dependent on only temperature ratio. Okay, so it accounts for change in gas density and used to define speed lines on component mapping. The third one is corrected fuel flow rate, that M mass of fuel, corrected mass flow rate, MFC dot, which is given with MF mass flow rate, actual mass flow rate times temperature ratio divided by radical of temperature ratio divided by pressure ratio. And that we can properly write MFC dot is equal to actual mass flow rate MF of the fuel divided by delta, which is temperature ratio, pressure ratio times radical of temperature ratio. So this is the relation. So MF is actual fuel flow. T naught is ambient temperature, P naught is ambient pressure, so that we can have this corrected mass flow, mass of fuel flow rate. Here it is not considered the, what you call that, air, but it is fuel only. The fourth one is corrected thrust. So FC is the corrected thrust in matching condition. So for any section I, we have to correct each of them from one point to another. So the corrected thrust specific fuel consumption is actually the ratio of corrected fuel flow to, actually this definition belongs to thrust specific fuel consumption actually. Okay, so in our case, corrected thrust is given by FC is equal to actual thrust F divided by pressure ratio. Okay, so FC is equal to F over delta naught. So that is at reference condition. Okay. So the next is corrected specific fuel consumption. So specific fuel consumption, SFCC, is the ratio of corrected fuel flow to corrected thrust. Okay, so which represents specific fuel consumption, which is equal to corrected mass of fuel flow rate divided by corrected thrust. Okay, so this ratio is called specific fuel consumption. Okay, so that specific, we know MFC is already given there and FC is already given. So we divide them and finally what we can get is specific fuel consumption. Corrected specific fuel consumption is equal to mass flow rate of fuel divided by actual thrust times radical of delta. That radical of delta, theta is the temperature ratio. Then we have thrust-specific fuel consumption. Specific fuel consumption is different from thrust-specific fuel consumption. In some cases, they are the same, actually. Actually, for jet aircraft, we use specific fuel consumption. No, it is just brake power specific fuel consumption for the reciprocating engine or turbine, actually not turbine, but propeller-driven aircrafts. But for the jet aircraft, we use thrust-specific because our